Good afternoon and welcome to another exciting telecom-focused OpenNebula webinar. I am Alfonso Carrillo Aspiazu, Principal Edge Solutions Architect at OpenNebula Systems. And today I want to make something that is usually complex and expensive, very concrete. How to deploy a full private 5G at the edge quickly and operationally. This work builds on what we presented at Mobile World Congress 2025 in Barcelona. And today we take a step further with a fully virtualized open vRAN and end-to-end automation. With OpenNebula, we automate the lifecycle of RAN components, CUDU, and the 5G core using reusable templates and cloud-like operations, reducing friction between lab and field and making timelines and cost predictable. And I am not alone. We are joined today by the IT's lab from the University of Malaga with Pablo Herrera Díaz and with Balázs Németh, from our telco engineer at OpenNebula Systems as well. We have prepared an end-to-end demo. We'll deploy the RAN on an edge cluster connected to the 5G core and validate basic KPIs. First, we will start with an introduction of what OpenNebula does and how we move to get here. And just if you're considering a pilot, you will leave a blueprint hardware requirements. We will leave a blueprint hardware requirements, reference topologies, and a realistic 90-day path to move from POC to operations. I think that with all of this having been said, I pass it over to Balázs so he can further drill down into what OpenNebula has done and how we have been able to integrate the SRS solution into our environment. Balázs?
Simplifying a complex infrastructure with a single and unified panel to automate and manage everything from on-premise to cloud environments. It's designed to be lightweight and flexible, freeing you from vendor lock-in while being easy to maintain. OpenNebula is proven to be reliable and scalable in large-scale, demanding production environments. Finally, this streamlined approach delivers an effective total cost of ownership compared to the leading alternatives. And next, I want to highlight what are the most relevant features of OpenNebula that enable deploying an open virtualized radio network and the private 5G on top of our software. So for that one of the most important points is that OpenNebula is a fully open source virtual infrastructure manager for cloud and edge computing use cases, and OpenNebula focuses on a simple and extensible architecture. This allows the integration of a wide range of infrastructure providers, cloud infrastructure providers, and vendor solutions. As well, multi-tenancy allows the separation of client workloads, also for the virtualized RAN components, which we will see in this webinar and the demo. As well, that it's a DevOps friendly tool, which because it supports the full lifecycle management of workloads, virtual machines with high availability, scaling, and recovery features, which makes OpenNebula a DevOps friendly solution. OpenNebula has a marketplace, an appliance marketplace, which makes the deployed solutions highly automated and possible to reproduce thanks to pre-configured virtual machines, which contain the appliances and makes them easy to deploy, even for multi virtual machine services. Also, the private 5G and the end-to-end virtualized RAN, which we are going to showcase here in this webinar, is a perfect example to demonstrate this quick reproducibility and a high degree of automation. As well, very importantly, OpenNebula supports high-performance virtualization use cases, such as PCI pass-through and SRIOV, and CPU pinning, huge pages, and so on, which are essential for meeting the very demanding performance requirements of telecom applications. We will see examples of how do we configure this in an automated way in OpenNebula for these specific use cases, and how this enables to realize this whole end-to-end picture that we are going to present here. So before jumping into the demo, here we have listed the full list of the hardware specification that we are using for this end-to-end deployment. So first, for the radio components, we use a standards-compliant Lighton Open RAN radio unit and the commercial off-the-shelf cross-core 5G smartphone as the UE, as the user equipment. And this entire virtualization stack runs on a server with equipped with 120 gigabytes of memory and 400 gigabytes of SSD storage with an Intel's own CPU. The network interface card is one in this demonstration is an Intel 810 network interface card with the GNSS capability. This is absolutely essential for the high precision timing, which is required between the virtualized radio component and the actual radio antenna. So here you can see the demo outline. So first, Pablo, our colleague from the University of Malaga, will give an architecture overview of how each component are deployed on top of OpenNebula, and how the other software components that our fully open source solution relies on, how they are packaged and orchestrated by OpenNebula. Then we will show the automation of how we configure the kernel virtual machine hosts with scripts, and then we will verify that the synchronization status between the radio unit and virtualized RAN components. So first, we will deploy these pre-built VMs, the SRS RAN project's VM, which is going to realize the 7.2 split of the ORAN architecture, splitting the DU and the CU. And then the 5G core itself is going to be served by the Open 5GS project that contains basically all of the 5G core network functions packaged into a virtual machine. And then finally, at the end of the demo, we are going to show an end-to-end connectivity. So basically, we are going to showcase how the traffic reaches from our private 5G network all the way from the UE, the radio network, to the 5G core, and broken out to the public internet. And with this, I give the floor to Pablo to show us the demo.
Thank you very much, Balázs. Now I will start with the presentation of the demo. Okay, this is the final demo of the 1S5G project, and we will be showing basically the virtualization of the Open RAN solution and the end-to-end test, including some measurements, KPIs of the performance. So this is the setup, okay? In this setup, we have done a very simple deployment of OpenNebula, and to do this deployment, we have used OneDeploy to automate the deployment. We have the front end here to control everything, and then just one KVM host, which is this one. This KVM host is very important because it allocates the two virtual machines that are needed for this deployment. One for SRS RAN for the radio part, and another one for Open5GS. In addition, Another important component is the NIC, the network interface card. It is a specific model because we need, just in this specific case for the demo, the GPS port to use the GPS as the synchronization source. It could be another one, but in this case, we decided to use this. And also support the PTP standards. The PTP standards are very important because these are required to extend the synchronization from the master clock, which in this case is the host, the KVM server, to the different components, to the radio, the light on, which is here, and the virtual machine, including the RAN, the SRS RAN project. In addition to the radio, we also have the commercial UV, as Balázs said. In this case, it's a crosscal, but it could be any additional, commercial UV. And optionally, just to show some parts of the demo, we will be using a spectrum analyzer to check the radiation of the solution and basically that the system is working properly, but it is not needed. Okay, pass this. Now I will start with the configuration of the different components. We will be accessing one by one, and we will be start with the KVM host to show the configuration, the different scripts that are there, and how to configure everything. So now we are here on the KVM host. Now we can access through SSH, and here we will start using some scripts that will be available for the OpenNebula community. And these are separated into the install scripts that are scripts to install the different components and the different requirements for the solution. And then we have also some performance scripts to improve the performance of the solution. So starting for the installation scripts, we have first the installation of the ICE driver. This is a specific driver for the NIC, the network interface card that we have. This NIC, okay, the driver is already installed, so we are just testing it because all the scripts in the folder have both functions. It's install the required drivers, and it also checks if they are not there. If they are there, it just checks it and confirms that the drivers or the different packages are there. So in this case, the driver is already installed. And now we move on to the different script, which is the Linux PTP. Linux PTP is the Linux package for synchronization, and it is also needed. We need Linux PTP in order to create later the grandmaster on the server and to expand the synchronization signal to the different components. It is already installed, so it is just checking it. And then a very important step is the installation of the virtual function. In this case, we have a physical card, which is the Intel NIC. We have 4 physical functions. And on the first one, which is the one connected to the radio and also to the virtual machine, we will be creating a virtual machine, a virtual function. This virtual function will be used to expand the synchronization signal and also to allow all other features like DPDK to improve the performance of the solution. So in this case, we will just checking it. We will not launch it because it is already done, but we can check with the link showed command that the virtual function is already created and it is installed on the physical interface number 0. Now we will start another one, which is the PTP Grandmaster. Now we had previously the PTP, the Linux PTP package, and now we are installing or configuring the server as a Grandmaster. This way, we will have the synchronization signal here, and then we will propagate it to the different components. We are selecting the first interface, and now the PTP Grandmaster clock is running. Now we can move to the performance scripts. The first one is just a configuration on the server, okay? Running this script, we're basically doing some CPU scaling, different configurations on the CPU. Basically, we are installing real-time kernel. In case it is not done, it will install it. But here we are just checking that the real-time kernel is installed. It is needed because if not, the system will not be working. and other different performance configurations on the server that are needed. It is everything done automatically. Now we can move to the radio, to the RU, to check the configuration, and also to check if the synchronization status is okay. It has a very, well, a bit different, it is not a Linux, this is another system, but it has a very easy commands to follow. And here, accessing the terminal, we can check the different configurations that are available on the radio. Here, for example, we can check the bandwidth, we can change the central frequency, different slots for the pattern of the solution, the synchronization source, which is very important. In this case, we have set it to PTP because it is the synchronization source we are using. And well, all the parameters you can see here. And then we will check the current configuration to give you an idea of the parameters with the different values that we have at the moment. For example, for the bandwidth, we have configured 100 megahertz. This is the frequency, 3.85 gigahertz, and the different IPs, the MAC address of the different components, and the synchronization source is very important, is PTP. Now, another important thing is what I said before. We need to check that the radio has been synchronized. It is now synchronized, so it means that the synchronization signal is coming from the grandmaster and it is reaching the RU, and all the packages are on time. So the status is synchronized, and it is needed because if not, if this step is failing, the solution is not working. So now that we have checked that everything is working on the radio, we can, well, this is just an optional feature just to check with the spectrum analyzer that there is nothing radiating at the moment. We have put the configuration of the spectrum analyzer of this on this central frequency, and we can check that there is nothing radiating here. In the 100 megahertz bandwidth, there is nothing radiating, because at the moment we are configuring the component, but the solution is not running yet. This is just to check at the beginning, where is the status of the spectrum analyzer. And now we can move to the dashboard, the OpenNebula dashboard. This is the front, and we will be checking in first the host. Okay, this is the KVM host, and we just wanted to show you here that the PC is configured, as you can see here. Okay, this is configured, and then we can move to the different virtual machine templates. Okay, so a very, very important part of this project is the creation of two appliances. The appliances that are basically virtual machines that are pre-configured with different parameters that can be changed in advance before deploying the virtual machines. And in this case, we have created two appliances, one for Open5GS and another for SRS-RAM. With this, we will avoid a lot of deployment time. We can configure everything in advance. So people that want to deploy this do not have to take care about the different configuration. You just deploy the appliance and everything will be working. So checking, for example, the configuration of the SRS-RAM virtual machine, the appliance, this is the way you can launch it, but we will use this just to check the different configuration. We can change the IP, the frequency band, in this case band 77, the bandwidth, 100 megahertz, the subcarrier spacing. This is the ARFCN, which is basically the conversion to the central frequency, PLNN, no? the identification of the network, and then this component is the SRS-RAM mode. This is important because the G0B mode includes both the DU and the CU. But if you want to deploy this separately, you can select CU or DU, but you need to deploy two components, one for the DU and another one for the CU, and then interconnect this with the different networks on OpenNebula. But for this demo, we will use just the G0B, including both. Okay, so this is just the sample of the different components. And now we would instantiate the virtual machines. We will not do it here, of course, but we will just show that the two virtual machines are created. And I will go deeper into the different components just to show the resources allocated first. For example, for SRS-RAM, we have allocated 32 cores and 16 gigas of RAM. Then we have two networks, one for management. This is basically to access through SSH to it. And then the backhaul. The backhaul is basically the interface between the SRS RAN, in this case, the CU, to the core, to the Open5GS, basically N2 and N3 interfaces. And then here the PCI, okay? This is the interface that we have created previously with the virtual function and that we use to connect the RU with the DU. And we can see that it is there created. And then on Open5GS, we have basically the same. We need less resources, okay? We only need 4 CPUs in this case for the Open5GS and the same amount of memory, 16 gigas. And for the network, it is also very similar. The management network to access it through SSH, and then the backhaul, which is the same one than in SRS, but on the core part. That is N2 and N3, but on the core. Now we can move to the different virtual machines. First, we will go into the SRS RAM virtual machine to check that everything is running properly. At the beginning, we will launch the stop script. We have different scripts here to automate the use of the appliance, of the virtual machine. One script to stop, one to check the status, and another one for starting the whole solution. So we run stop at the beginning to basically to check that everything is not running. And we can check that actually it is not running because with the showing configuration script, we can check that yeah, the SRS run is not running. It is a stop. And if we want to run it, we can just use the start script. We just select that we don't want to modify the configuration. We are using the default configuration, but if you want to change it, you can do it, and you can change the frequency, you can change the bandwidth, and whatever you need. But we have done it previously on the appliance, so we don't need to do it now. So we run the system, and now we show the configuration, and we check that now. Okay, it has a lot of more information, but at the beginning you can check that the status now is running, so the solution is working. Now that the SRS run is working, we can check on the core, because if the radio is up now, we can check on core. Okay, this is Open5GS. Open5GS, in Open5GS, the different functions are 5G functions like the AMF, UPF, etc. Works as services. No, so each service is a function. Okay, you can see here all the different services running. All of them are up and running, so that's fine. And now we can check, for example, the logs of the AMF to verify that the radio is attached. We can see it there, okay, the G0B is 1, so we have the G0B connected to the core. And now we can also move to the dashboard of Open5GS. This is just following the documentation of Open5GS. It is very easy. We have provisioned UE, this one, okay? You have here the different configuration, the IMSI, the K, the OBC, the different, well, you can put the fixed IP on the UE, everything you can configure on the UE. And once it is on the spectrum analyzer, we can check now that the radio is radiating now. Not a lot, because we are not sending traffic, and this is just the SSB signal, but the radio is up. And now we can use, this is a remote access to the UE, and we are using a KeySight tool, this is Németh Handy, to connect the UE and check if the radio is working properly. So we basically remove the flight mode. And now we can check here. We will force just the standard mode just to save time on the UE connecting to the radio. And now you can see the different exchanges of messages. And now the video session is accepted. You can check that the UE is connected to the internet, and we can try testing it on the browser, for example, accessing the OpenNebula website. Okay, you can see that the end-to-end connectivity is working properly. And of course, we can do also a speed test to check the performance. We're doing the default one on the browser, and we can see that the performance on the UE is quite good. It's like 250. And now on the spectrum analyzer, we can see that we are using the full 100 megahertz bandwidth. So the solution is working properly. It is running on a virtualized solution. The end-to-end test is working fine. Thank you very much.
Yeah, thanks a lot. And here you can see the references and resources which you can use and refer to if you want to get more information or you want to reproduce this whole end-to-end solution in your environment. Here you can see the deployment guide for the solution that basically Pablo showed us, and and with the detailed scripts and the configuration parameters needed. You can also find here the link to the blog post that details a bit more of the solution that you just saw. And then also, most importantly, here you can find the links to the appliances, the SRS-RAN and the Open5GS. On GitHub, you can inspect the documentation related to which parameter exactly, what do they mean, and customize anything if needed. But most likely for reproducing the solution, you would only need to access the marketplace. So those links are what an actual OpenNebula instance would use to access and import directly these virtual machine templates, so you can deploy it in your instance. And then all of these components are fully open source and available for free, so you are ready to deploy it in the new environment. And this project has been made possible thanks to the OneEdge 5G project. So this concludes our webinar, at least the presentation part. So now we can jump into the questions. If anybody has anything to ask, we have some time to discuss them.
Set up. Pablo, you there?
Yeah.
Balázs, maybe you can answer.
Yeah. Yeah, let me know. Do you have some question?
Yeah, the question was, we see that we have, used the Lighton RU, and talking to some people interested on doing OpenRAN setups as this. Is there any other type of antenna that we can, or RU that we can use that we have tested or proved?
For now, for the moment, not. But basically, our integration to RUs relies on the SRS RAN integration, and that one is not only the Lighton. So we can refer to the SRS RAN project and see other available RU integrations there.
Okay, good. I see there's no more questions arriving. Well, so thank you very much for attending. And if you have any questions that pop up later on, we have our contacts on the description of the video, and you can send them forward. You can forward them, and we'll be more than happy to answer any doubts or give you more detail on what the setup that we used, how we proceeded, where are we going from here, all those nice details. Thank you very much.
Thanks a lot.